Hello everybody, welcome to your Lecture 8 skill check. Here we're going to start the first of two, maybe three skill checks where we go over the concepts involved with simple linear regression. And so in this scenario, we're imagining that Letitia selected 50 days at random over the span of a year, and on each day she measures two things. She measures the average daily temperature for that day. That's going to be a predictor. And then she also measures the amount of money she spent that day on heating costs, on heating her home. That's the response variable. Now, I generated the data using Minitab. This is what the data looks like, as you will have seen in the assignment. I want to explain how this data was generated because I think that will go a long way to help you understand this whole linear regression idea. So I'm going to show you Minitab and what the data looks like in Minitab. So here it is. You see there's 4 columns. Now you might be surprised by that because the graph only shows a graph of X versus Y, where X is the daily mean temperature and Y is the daily heating costs. That's what you see in the graph, but the question is, how do I generate these daily heating costs? Well, the first thing is to generate some daily mean temperatures. And so this column consists of values that were generated using a random data generator. And so you can see some of these values are positive. Those would be daily mean temperatures for data collected in the spring and summer. And some of them are negative, and those would be the winter values. Right? So these are just random values that represent random daily mean temperatures. On the far side here, we have our daily heating costs, and those are computed by combining two things. We have a systematic component and a random component. Now, hopefully, these words sound very familiar to you. Let's see how we get these systematic components. So I'm just going to go up here to calculate and calculator. And so this function here, this calculator function, allows us to use existing columns to produce new columns. And so the way systematic was produced is I started, so okay, I'm storing the data in systematic, which is here. And the way it was produced is I made up a linear equation that would relate daily mean temperature to a systematic cost. And so it was a simple linear equation. It was something like 0.15 times the daily mean temperature. And I think it's possible I added a constant onto there. I don't recall exactly. I think I might have added something. Let's say I added 10. Right, so the point is, this component is systematic. This is going to be one part. This column C2 is one part of the daily heating costs. It's the proportion of daily heating costs that is systematic, meaning we have a simple function that relates daily mean temperature to that daily heating cost. Right, so that's the systematic component. What about this random component? Oops. Okay, what about this random component? Here, when we do the random component, all I'm doing is producing random variations using a normal distribution. And so here I think I used a normal distribution. I think the mean was 0 and the standard deviation might have been, I would guess, about 3. Maybe smaller, maybe it was 2. Doesn't matter. The point is, all of the data in this column is purely random. Now, let's put that together. So once more, we have a systematic component where we take each daily mean temperature, we multiply by a slope, and we add a constant. So these are generated from the predictor variables using a linear equation. And to that, we're going to add purely random numbers. Together, those give us the generated daily heating costs. And so here in this column, the way this column was calculated storing in daily heating cost. Here the expression is simple. We just take the systematic component plus the random component. Whoops, silly. Plus the random component, like that. So putting these together, if I press OK, I'm going to get these daily heating costs. So hopefully seeing the way the data was generated can help you understand how, when we're looking at two quantitative random variables, in this case, daily mean temperature and daily heating costs, if there's a linear relationship between them, then that relationship can be expressed as the sum of two things. One is a systematic component, and one is the purely random component. Okay, so I hope that gave you a little bit of insight into this whole linear regression concept. Anyways, so let's just continue now with the questions. So the first question is this: looking at the scatter plot, it appears that simple linear regression is an appropriate model for this data. But can you explain why this is the case? Well, this is a fairly easy question. The main idea is the data needs to look as if there is a linear relationship. Now, I just made a change to the scatter plot. This is an example of a scatter plot where fitting a linear model to the data is not appropriate. And why not? Because you can see the trend in the data is not linear. It is distinctly non-linear, or you could say it's some kind of curved relationship. Now, what we want to see is a linear relationship of some kind. There must be evidence of that in appearance before we can go ahead and use linear regression to come up with a model. So again, it is only appropriate to fit the linear regression model when the two categorical variables appear to have a linear association. Here, the association does appear to be linear. There's a distinct linear trend, a negative trend in this data. And so we can fit the model. It's as simple as that. The second question has to do with looking at output from Minitab and identifying the coefficients for that linear model. And so here too, I'm going to show you in Minitab how you would go about getting those coefficients. So here we're going to use the same data. We go up to statistics, so stat, we pick regression, and we're going to pick here regression and then again regression. And then again, fit regression model. So we're going to fit a regression model. And so here, all we have to do is identify which is the predictor and which is the response variable. So see here, responses, we pick daily mean temperature. Sorry, that was a mistake. Daily heating cost is the response, and the predictor is the daily mean temperature. So we select those. Then we have various options that we can choose from. But in the end, you're going to press OK once you decide your options. We don't need to talk about the options right now. And you're going to get a bunch of output. So this output, now I'm looking at right here, that's the most important one for the question we're currently working on. Let me just make that a little bit larger. Right, so this is the table that we need to know how to interpret. And that's the same as the table on the slide. So we can go back to the slide now. And so what do we see here? We see two words, constant and daily mean temperature. So what do these mean? Well, the constant is the intercept. It's the y-intercept for the model. In other words, it's the B0. The daily mean temperature, you will recognize, is the predictor variable. And so the coefficient that goes with that is the slope of the linear equation. And so that's really all you need to know for this question. You need to know how to pick out these two parameters, the intercept and the slope of the model. So let's just remember that the predictor variable is the daily mean temperature. The response variable is the daily heating costs. And so we can write now we can write our simple linear model that comes from this Minitab analysis. So we put in the intercept, we put in the slope, and next to that we put in our x, our predictor variable. So this is that simple linear equation. And again, the point is to be able to read it from a table like this one. I probably should mention, obviously, there are other things in this table, and probably by the time you're watching this, you're going to know what all of these things are. But for the purposes of this current skill check, we don't need to worry about that. And let's see what else, right? So we were asked to provide an interpretation of the intercept and the slope. So here, the intercept, remember that the daily heating cost is in dollars. So the intercept here is telling us that the average cost when the temperature is 0 is $10.15 per day. And how do I know that? Well, see, if you put x equals to 0, that means the daily mean temperature is 0. When that is the case, y hat is just equal to this intercept. So again, the intercept, $10.15, is an estimate of the mean daily heating cost when the daily mean temperature is 0 degrees Celsius. The slope, which is the other number here, the slope is about 31 cents per degree Celsius. What is that telling you? This is an estimate of the reduction in the mean daily heating cost with each degree increase in the daily mean temperature. Right, so it's saying that for every increase in temperature by 1 degree, your daily mean costs will decrease by this amount, $0.31 or 31 cents, in other words. Right, so that's how you can explain the meaning of these things in words. I think it helps to look at a figure. So we're going to look at a diagram, and I'm going to draw some pictures to interpret geometrically what the intercept and the slope are. But before I do that, I want to show you where this plot came from in Minitab. So this is not just the data, the scatter plot of the data, but we also have a line of best fit drawn through the plot. So I just want to show you how you can get that. So here I'm just going to erase this current analysis. And here we're going to go again. We're going to go stat, regression. And this time, instead of picking regression, we're going to pick fitted line plot. Here, the response variable is the daily heating cost. It's been already selected. The predictor, daily mean temperature. We're going to choose a linear regression model and press OK. And in the end, you get some output, which is similar to the things we just saw. And you also get this fitted line plot. So that's how you can produce that kind of figure. So let's now use that fitted line plot to talk about the interpretation of intercept and slope. So first thing to recognize is where the vertical axis is. Here, where x is equal to 0, we have a vertical axis. This is the y-axis. And you'll notice there's a point where the line of best fit crosses that y-axis. That place, that is the y-intercept. That is the intercept of the model. And so if you want to know what the y value is at that intercept, you trace over to where we have our scale and you just read it off. And so we can see that this intercept is where the y value is $10.15. Now, what about the slope? Well, usually we just represent the slope with a triangle. And the idea behind the slope is with every 1 degree increase in temperature, we expect to see a decrease in the mean daily heating costs of about 31 cents. Right? You know the slope is negative because the line is going down as you move from left to right. The slope would be positive if the line was going upwards as you move from left to right. Okay, probably everybody already understands that. So let me just continue to the next question. So question 3, it's asking you, it's giving you a coordinate and asking you to calculate a fitted value and a residual. So this is something you've done many times in 2208. So here they're saying that one day in March, The daily mean temperature was 10.82 degrees Celsius, and the daily heating cost was $9.13. And we're going to calculate the fitted value and residual error for this observation. So again, it's good to remind ourselves that X is the predictor, it's the daily mean temperature, Y is the daily heating cost, and we have our linear equation. This is our equation for the line of best fit for our data. And so to estimate an estimate of the mean response, we take this equation, and in place of X, we put in the X value that was given, 10.82 degrees Celsius. And so once we do that, we just have to multiply these two numbers together. This is the slope, the minus 0.313. Multiply that with the temperature that's given, the daily mean temperature. We get 3.387, and we subtract that away from the constant, and we get in the end, it says here 13.54. Clearly, that's not correct. Let me just go back and fix that. It appears that I added instead of subtracted, which is a bit silly, but that's okay. It's easy to fix. So let's go 10.151 minus 3.387, and we get 6.764. I'm going to round that to 2 decimal places since this y hat is in units of dollars, and so it doesn't make sense to have more than 2 decimal places. Right, so that's the estimate of the mean, and now I got to fix the residual. So how do we get the residual? We take the observed value, which was given to be $9.13. We subtract from it the residual, we subtract from it the fitted value, which is 667, and in the end we'll get that residual value. So let me just do that. $9.13 minus $6.67, $2.46, 2.46, and that is a positive value. Okay. So despite the fact that I got it wrong the first time, well, now we can see the calculation is fairly straightforward. So hopefully you are good with that. Let's go on to the next one. Question 4 is talking about the partitioning of the variation. Now this is something that you may not have looked at very closely in 2208. In my class I talked about this a little bit, although I did discuss it in a different way than the way we're talking about it now. And that's partly because in 2208 I didn't want to introduce the idea of sums of squares. But for this course, for 2209, we need to talk about sums of squares, not just for regression, but also for something called analysis of variance, which is coming. So that's fine. The point is, we have observations, and those observations have some amount of variance. I keep saying variance. I have to be careful. Variance is one thing. What I'm talking about is variation, a measure of variation. You can think of it as a measure of spread, or even as a measure of uncertainty. So we have some variation in our observed y values. This number, the symbol is ADJSS. So the SS represents sums of squares, as we discussed in class. The ADJ just indicates there's been some adjustment to those sums of squares. We don't need to worry about that. The key point is to understand that the sums of squares is a measure of, I don't want to get it wrong, it's a measure of variation. And this number here, 279.24, represents variation in the observed values. Now, this variation, when you do the regression, is going to be split between a systematic component of variation and a random component of variation. So that reflects the way the data was generated, right? So let's just look at that once more, just to remind you. The way this data was generated is this daily heating cost. These are the y values. These y values have some variation. These y values were generated by taking a systematic component and adding to that something that was purely random. The systematic component being a linear function of the predictor variable, daily mean temperature. The random component being purely random. And so the systematic component has some variation. The random component has some variation. And that's what these sums of squares measure. So we have a total, which is being split between something that's systematic, we call that the regression component, and something that is purely random, we call that the error component, right? So the regression component is essentially the variation in the fitted values. And the error component is just the variation in the residuals, right? So if you add these first two numbers together, you will get this third number. Right, so all of this is explained here. So it says the sum of squares provides a measure of variation. And I can see I made another little typo, so I'm just going to take that out. Put that here. And yeah, I think I appreciate your patience with me. I don't want to have to re-record things because of little errors I make. So I'm just going to make the corrections as I go, if you don't mind. Anyway, so the sums of squares provides a measure of variation. The variation of the observed daily heating cost, which is the Y value, is this 279.24, this number here. The fitted values account for most of this variation. See, the fitted values account for most of this variation. This is the systematic component of variation. The remaining 47.72 points of variation, I guess you could call it, this remaining number represents the variation of the residuals, and this is the random component of variation. Right, okay. Right, so here, question 5, it says use the sums of squares in the table to calculate the coefficient of determination and the regression for the regression model. Okay, I see, wow, but there's a lot of typos here. That should be sums of squares. That should be regression model. So we're going to calculate R squared, and we're going to talk about what that R squared means. Right, so R squared, this is simply the proportion of variation in the observed values that's accounted for by the regression, or in other words, by the fitted values. So we simply just take the variation in the observations, put that on the bottom. On top, we put the variation in the fitted values. And so it's 231.52 on top, 279.24 on bottom. We get that ratio. We do the calculation. We get, in this case, 0.8291. Now, I want to show you in Minitab how you would go about getting that, or where it appears. So essentially, if I could just pull this down, please. Thank you. Okay. Essentially, we go to Stat. We go to Regression. We can go to, there's a few ways to do it. Let's just do fit regression model. Everything is already set here, so I'll just press OK. And you're going to see, there it is. So in this table, the model summary, they give you a few things. First, they give you, this is the standard deviation of the residuals. You can see that's essentially 1. And next to that, you get the R squared, and then you have an R squared adjusted, which we'll talk about at some point, and the R squared predicted. These are things we'll talk about later in the course. For now, you just need to understand this R squared. You can see it's 82.91%, and that should be, yes, it's the same as what we just calculated. So just to convince you of that. Okay. What's next? I see a big blank slide, so let me try to remember. Yes, so at some point in the analysis, you need to confirm that all of the assumptions required to do linear regression are satisfied. The first assumption was that there needs to look, the data needs to look like there is a linear association. So we checked that out already, but we have other assumptions that need to be checked as well. So the first one is the one we kind of checked already. The scatter plot must suggest a linear association. This is called the linear enough condition. I think quite often, at least at the Mount, we call it that. And we often check this by looking at the residuals. And the point is, we should see no trend in the residuals. So we're gonna see that in a moment. I should point out that when you start the regression analysis, it's okay to just look at the scatter plot of x versus y and just say, does that look linear? I guess it does. But you should be aware that sometimes the scatter plot can look as if there's a linear association, but then when you look at the residuals, you can see that that assumption actually wasn't valid. In some ways, the residual plot is in some ways, it can reveal non-linear conditions more easily, make them more obvious than the scatter plot itself. And so in this case, we're not going to see actually any violation of this rule, but at some point I'll show you some examples of that. Anyways, first condition. Second condition, the spread of y must be roughly the same for all values of x. And this is called the constant spread condition. Sometimes at the Mount they call it the plot is thickening condition. But the point is the plot should not thicken. There should be no, what you might have called in 2208, there should be no trumpeting. The spread should be constant. So I call it the constant spread condition. Right, so that can also be checked by looking at the residuals, as we will see. We also need to make sure there are no unusual observations. So in the last class, I think we just did this yesterday. If you're looking at this on Friday, what is this? February, what? Oh, I don't remember what today is, just a sec. Okay, today's the 9th. So if you're looking at this on February 9th, then yesterday in class, you would have seen a discussion about this third point. Large residuals and leverage points that are potentially influential. So we need to check for such unusual observations. As we'll see in this case, there are no unusual observations, but in class yesterday, we did see a case where there were unusual observations. And then the new condition, which is something you didn't talk about in 2208, is that the residuals themselves should be consistent with the normal distribution. In other words, there should be evidence that the residuals are normally distributed. That's a key assumption for the model that is required in order for us to make inferences from the regression model. And I guess I should point out that in 2208, you didn't make any inferences about the regression model. In this course, we will be making inferences, which again, if you're watching this on Friday, February the 9th, we talked about inferences. We started to talk about it in class yesterday. Okay, so whatever. Here's what we need to look at. We need to look at the first two plots that you can see here. We have the first one is a normal probability plot. The second one shows you the standardized residual versus fitted values. I'm showing you 4 plots here because I've noticed for this course on tests or quizzes, they often show you all 4 of these plots, when in fact you really only need the first 2. Sometimes the histogram can be useful, but it's the first 2 plots here that are most important. So what do you need to see in these 2 plots? Well, remember the conditions. We need to see that the residuals follow a normal distribution, or at least are approximately normal in distribution. We need to see that the residual plot has no structure. So in other words, an indication that the linear fit was good enough. And we need to see also that the spread in the vertical direction of the residuals is roughly constant. So all of these things we can see here. So the first thing is the approximately normal assumption. So in this normal probability plot, we're looking at standardized residuals, and that just means you take each residual, subtract the mean residual, and divide by the standard deviation of the residuals. And so you can see that most of these residuals are within plus or minus 2 standard deviations of 0, which is exactly what you would expect if the residuals followed a normal distribution. Furthermore, these residuals, these points, in this plot, they make roughly a straight line. And if that's the case, then you could say, yes, the distribution of the residual errors in our model, these are approximately normal. And so that condition is satisfied here. And by the way, on the vertical axis, what we're doing is we're comparing the standardized residuals with the quantiles of a standard normal distribution, in case you wanted to know. Now, if you don't really know what all that means, that's okay. It is a bit complicated. The important thing is, one, you understand if the dots are in a straight line, then normality is indicated. And two, I need you to understand that this red line is not a line of best fit. This plot is not a plot showing you a line of best fit. It's not a regression. It's something else. It's a normal probability plot, right? And I'm only saying that because I noticed on the final for 2208, a lot of people thought this was a regression line, but it's not. So I just wanted to point that out. The linear enough condition, the best way to test for that, just by just inspection, by just looking at a plot, is you should see that this data cloud, these are the standardized residuals versus the fitted value. You could also have a data cloud where it's the standardized residuals versus the predictor, the X value. In both cases, this data cloud should look flat. It shouldn't look like there's a linear trend or any other kind of trend. It should look perfectly, well, more or less flat, let's say. So for example, if this data cloud was oriented so that it looked like there was a positive slope, that would be a violation. You would say, no, the data, the original X versus Y was not linear enough. And we can see that because there's a trend in the residuals. You want to see no trends in those residuals. And here, that is definitely the case. We see no trends in these residuals. So that's the linear enough condition. The second condition, the constant spread, or I should say the third condition, is you see no thickening of the plot or what they call trumpeting. And here you can see that the spread in the vertical direction of these residuals is approximately constant. And so that condition is satisfied. So here we can say then from this analysis of the residuals that it was appropriate to use a linear regression model for this data. One more thing I'll point out is here we have a histogram. And if someone were to say this data doesn't look normal because the histogram is bimodal, I don't blame you for that. The histogram looks bimodal. Very clearly it looks bimodal. In fact, it is bimodal. However, you should be aware that histograms are kind of finicky, I guess, or they're sensitive to various parameters you use to make the histogram. Let me say that in English. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Here we have 10 bins. So the histogram binned the data with 10 different bins. It sorted the data with 10 bins. If you were to use, say, 6 bins instead, this gap would disappear and the histogram would look like it's unimodal. So the point is, histograms aren't really the best way of assessing normality, especially if there's not many data points. If you had 1,000 data points, a histogram would be a good way to assess normality. But with only 50 data points, you can get a histogram that looks funny like this. It looks like it's bimodal, even though the data itself, the residuals themselves, do in fact follow fairly closely a normal distribution. Right. So that's why we use a normal probability plot to assess normality. Anyways, I said a lot. I hope most of that was helpful. Stay tuned for more. Bye for now.